Have you ever wondered why leaks in your system always seem to occur at night and in the middle of the night? And so your call outs in the middle of the night tend to be the most expensive because you're rousting people out of bed. So why is that? And the answer is relatively simple when you think about it. It is due to overpressurization of the lines at night. Hey everybody, I'm Tom Ballard, the Groundwater Guy, and today we're going to talk about pressure modulation and its role in reducing non-revenue water for small water systems. And this is a huge deal. And overpressurization at night, it really comes down to the fact that a lot of systems do not change their water pressure. So they're running water pressure during the day. That's going to be where you're getting the most demand in your system, and you're going to maintain that water pressure. But at night, when not so many people are using the water system, you're going to be overpressurizing your lines, which can lead to pipe breaks and cracks and leaks that can be they can become full blown emergency call out. So that's the deal with pressure modularization. We're going to dive into a little detail here on that. So let me dive in and get this. Well, I guess that doesn't. Let me. Eh, All right, here we go. Sorry about that. So, pressure modularization, we're really going to look at a data driven strategy for small water utilities. And like we do on so many things, we're really looking at incorporating data driven strategies and AI into the Internet of Things into our management process. So pressure modularization is really a cost-effective strategy for non-revenue water reduction, and we're basically trying to optimize our pressure management. So um, let me just move on here. So why pressure modularization matters? It's basically a strategic solution. So for small water utilities facing infrastructure aging and tight budgets, non-revenue water can, in some systems, be up to 25 to 50% of your total water supply. So you're really losing a lot of money. It's a significant financial drain. We generally want that to be around the 10% area, sometimes 15%, 10 to 15% in there anyway. So when it starts to get above that, now it's making a financial impact on us because we're paying to produce the water, but we're not getting any revenue from it. So, fortunately, with pressure modularization, this is something that we can really do that makes a big impact on our non-revenue water losses. So that's what we're going to explore today. So. Pressure modulation, by the way, is recognized by the International Water Association, the IWA, as a foundational element of optimal water distribution management. So the key benefits for your small water utilities, it dramatically reduces water loss from leaks and trying to get us down to that 10 to 15% non-revenue water range. It cuts main break frequency by 18 to 30% to reduce system stress. So you're not applying as much stress on your system when you're overpressurizing it. And then that's going to reduce main breaks. It lowers your energy cost by reducing pumping requirements, extends your asset life, deferring costly capital replacement projects. It's scalable. You can start small in a certain pressure zone. If you're broken into pressure zones, you can start in one area and start adopting this and then expand out as you tweak your system. So you can do a pilot study and then expand that out. And it's cost effective. It'll get you an ROI often with 3 to 5 year or less payback. So it's really one of those low hanging fruit things. Non-revenue water is a low hanging fruit thing. I always say because you can spend a little bit of money and really get a substantial ROI. When you're looking at these strategies to reduce non-revenue water, and then we can move on to tackling tougher problems. But that'll get some money back in the bank for you. All right. So the problem with unmanaged pressure costs, we look and see that there's a lot of small water systems that may have 25 up to 50% non-revenue water. This is a huge deal. So one of the primary culprits is excessive pressure. So non-revenue water is water that's treated and pumped but lost before reaching paying customers, and represents a big financial drain on your system and a waste of your resources. That's water you basically paid for that you're not getting any revenue for. So unmanaged system pressure forces water out of existing leaks continuously. So you may have a small crack in a pipe, but overpressurization then starts to expand that leak. It pushes water out, and eventually, over time, it becomes a main break. So that's what we want to avoid. So constantly elevated pressure places relentless stress on pipes, joints, valves. They're not designed to do that for take those pressures for long periods of time. So you want to get it down to where it's more manageable and less stress on your distribution lines. It accelerates infrastructure decline and increases main break frequency. Significantly drives up operational and emergency costs because being called out at midnight or 3 a.m. is certainly a lot more expensive than if the break occurs during the day. But usually it's going to be at night because of overpressurization. So that's money that's flowing out is non-revenue water, and pressure modularization is a big step to fixing that problem. All right, there's a direct link between pressure and water loss. And this is basically just basic physics. Higher pressure inside pipes creates greater force pushing water out any available open. So, like I said, a small um, when you're overpressurized, that's going to turn that small crack into a bigger crack, or at least expand it out while that pressure's on it, and you're going to be leaking the water there. So, and it's not a linear relationship. It's actually more of a logarithmic relationship, or at least a curve here. You can see in the diagram here. So, um, leak in plastic pipes, they can expand under pressure. A 10% increase in pressure can lead to much more than a 10% increase in leakage volume, as shown by this graph here. And constant elevated pressure fatigues infrastructure over time, and even mild operational stresses can trigger failures and weaken pipe, especially over time as this overpressurization continues at night and then during the day. Then you back off a little bit, then it's overpressurized again at night. Going through those cycles then really creates a lot of stress on your system. So the proven impact of pressure management, we've seen anything 18 to 30% reduction in main break frequency, and 10 to 15% overall water loss reduction. Uh, Research shows that well executed pressure management programs deliver significant, measurable reduction in both leak flow and infrastructure failures. And this is where the data driven component comes in, because this is measurable stuff that you can take back to your board and report on your investment in pressure modularization and how it's the ROI you've achieved and how it's helped your bottom line. So it's always good when you can do that with your board, because you're justifying those expenditures and you're showing a real return on investment, which is what they want to see. So beyond leaks, the high costs or the hidden costs of high pressure. So there's a financial impact that extends far beyond lost water. These secondary costs are often hidden within other budget categories, but they're equally detrimental to utility operations. One is the accelerated infrastructure aging, and let's face it, most of our infrastructure probably is being pushed to the limit, and we might be beyond the limits on that infrastructure and your distribution piping as it is. So by over pressurizing those already weakened lines and aging lines, you're going to definitely set yourself up for some leaks and main breaks that are going to cost you money to repair. Increased operational costs. Maintaining unnecessarily high pressure requires pumps to work harder, run longer, directly increasing electricity bills. So, and each pipe break demands emergency response that's definitely going to cost you more with overtime and the repair materials, vehicle fuel, all that type of thing. degraded water quality and safety. When you have a line break and you can start to get contamination in the lines, now you got to go in and you have to disinfect everything and chlorinate everything as you do these repairs. So, and in some cases, you may have to issue boil water orders, and boy, everybody hates to get a boiled water order, and it makes the utility look bad. Don't want to go there if you don't have to. And service interruptions and lost trust. So we have our customers out there. You're having line breaks. They're losing water pressure or losing water completely, and so you're losing that trust of your customers. And we want to maintain that trust. So by keeping the water flowing, that's how you're going to keep that trust. So for small water utilities with limited resources, these compounding costs can create a cycle of reactive crisis management rather than proactive system stewardship. And that's really what this is all about, the data driven approach. We're trying to go from reactive, where we're just fixing leaks as they occur, to proactive, so we can anticipate where they're going to occur and take things taken care of ahead of time. And with things like pressure modularization, now we're kind of forestalling, even and as we do our predictive analytics, we're now able to stretch out the life of those aging assets, as it were, and get some additional benefit from that. All right, so understanding pressure management and modulation. So, what is pressure management as distinct from pressure modularization? So, the IWA definition: the practice of managing system pressures to the optimum levels of service, ensuring sufficient and efficient supply to legitimate users and consumers while reducing unnecessary or excess pressures. So, that is pressure management. So, what is pressure modularization then? And so pressure modulation is the operational technique that we use that dynamically adjusts through the PRV, or the pressure regulation valve um, settings in response to changing system demands. So, and we'll look at the different PRV valves out there, but that's going to be your main technique. Um, so the core principle is really lower pressure during off-peak hours. So overnight usually is when that is, and raise it during peak demand periods, so you're maintaining steady water pressure and not putting that stress on the pipes. Smart approach eliminates excess pressure while maintaining minimum required service levels. And data driven, it uses real time monitoring to optimize pressure 24/7. So we'll look at the various ways, the different types of PRV valves are out there for tackling these different approaches. But you can already see kind of where we're going with this. So the key benefit is we dramatically reduce water loss during low demand periods when leaks flow unabated because of the high pressure. All right, best management practices. We got 6 of them here. And so a systematic data driven approach to implementing pressure modulation in small water utilities. This is a 6-step framework we're proposing here as a best management practice, or best management process, or BMP, as people like to shorten it up. So, number one, we're defining objectives. We're going to do our system assessment, create the pressure zones, modulation strategy, data driven decisions, and then continuous improvements. Always continuous improvements. You're probably not going to get it right the first time, but we're going to loop back around and make adjustments and improve things continually over time. All right, so let's look at these in a little bit more detail. Defining clear objectives. We need to know what we're going to doing before we start. So we want to identify our system pain points and establish measurable goals. You can't measure progress without having the goals and being able to measure them. So if you can't measure it, you can't improve it. So our goal then: reduce leakage, lower non-revenue water through pressure optimization, extend pipe life, minimize the bursts, so decrease the frequency, lower energy costs as part of that, and improve service reliability. So we're not popping these leaks at night. So maintaining a stable pressure for customers. So Number two, system assessment. Now that we've defined our objectives, we want to move on to system assessment. What do we have going on in our system, and how does that fit in with our objectives? So, we want to do baseline pressure mapping. So, we want to deploy portable pressure loggers at hydrants to capture true pressure fluctuations over a period of about a week or so, maybe 2 weeks, to kind of get an idea of how the pressure fluctuates and where it's highest and what your system looks like in your pressure zones. So identify zones, map high and low pressure areas, and critical customer locations. That's going to be important. If you have big customers like companies and businesses and stuff, you want to make sure they're taken care of too. So, SCADA data review, analyze existing system data from pumps, tanks, and sensors, and make sure that your SCADA is capable of handling internet connected sensors and PRV valves. So that's going to be important. Is our SCADA up to the task? Compare to the standards, verify compliance with regulatory minimums. So we want to make sure we maintain pressure according to our regulatory standards and assess our critical points. Identify the highest elevation and most disadvantaged service points and figure out how you're going to tackle that. um, Steps 3 to 4, pressure zones and modulation strategy, creating pressure zones and place the PRVs, the pressure reduction valves, or pressure regulation valves. I think it's better called pressure regulation valves because you may adjust the pressure up. And if you have automatic ones, you're going to adjust the pressure up during the day and lower it at night. So I think it's better calling a pressure regulation valve. But that's just my little quirk here. So you want to segment your distribution system into logical pressure management areas where pressure can be independently controlled. A lot of small water systems already have this, but if you don't, then it might be worth strategizing how can you do that logically and make it work. Sometimes it doesn't work, but for the most part, it's a lot easier to manage even a small system if you have logical pressure management zones. You want to divide the system up, based on topography, elevation. You want to install the PRVs at strategic entry points into each zone because that's going to control the pressure. Position the PRVs to control flow into lower elevation areas where pressure builds up. So you may have not just at the entry point, but you're going to have PRVs at other locations in your pressure zone, and calibrate the PRVs to maintain safe downstream pressures while eliminating excess pressure. Ensure redundancy and monitoring to protect service reliability. All right, so now then we want to select our modulation strategy. So choose the appropriate control method based on your system data, operational constraints, and available resources, and basically, what you can afford is what some of this step comes down to. So we got a number of approaches here. We can generally most small systems now basically just have uh, a PRV that is basically set at one pressure, and we don't adjust that much. So we want to go to adjustable pressure. So there's a number of techniques to handle that. So time-based modulation is one, and this is probably going to be your cheapest one because you're just basically going to have a PRV with a timer on it, and it's going to basically adjust pressure at preset times during the day, and that's going to lower your pressure overnight, raise it again during the day, and you're going to basically set that, and that's what's going to happen. Those are going to be your cheapest automated PRVs. Is going to be the time based modulation. Getting a little more complex, we have demand based modulation. So you're basically adjusting pressure dynamically based on real time flow data. So you're going to have flow meters that are tied into your PRVs, and now you're going to adjust the pressure in your pressure zones using the flow data, and that's going to be happening continuously as the flow data is fed into the PRVs to maintain the same water pressure. So we want to establish protocols for regular inspection, calibration, data review, and implement fail-safe measures to ensure service isn't compromised by controller failure. So always have some backups and stuff. Um, so key success factor here, you're going to want to start with one well-defined pilot zone, one pressure zone, and really work with that, work the bugs out there before you start expanding that out. So that'll really help work the bugs out, and you're always going to have some things you're going to have to adjust in any of these things. A rollout rarely goes perfect, so doing a pilot in one area generally is the best way to approach this. All right. BMP steps 5 to 6, data driven decisions and continuous improvement. So, data driven decision making, this is a big part of what we recommend for even the smallest water utilities is you're making decisions based on actual data and not guessing and not trying to pull it out of your head from memory. You're dealing with actual data. And you've recorded that data, you have it accessible in a database or spreadsheet or something that's accessible. So you're dealing with real data. So so you're going to want to integrate your pressure modularization into your utility's regular data review cycle to track performance and guide operational adjustments. You're going to want to have some standards or some key performance indicators or KPIs. We always recommend having KPIs for these things. So water loss is going to be one of these. You're going to want to compare before and after non-revenue water and your minimum night flow or MNF. So that's going to be your minimum flow at night, and you're going to compare those. You should see some improvement there. Leak frequency, track the number of main breaks and repairs per month. You can actually track it per mile per month. There's a lot of different ways to get at that, but basically you're actually tracking with real data and can look at the trends. And that's always what's important in data-driven decision making is looking at the trends. Energy costs, you're going to want to monitor those, customer feedback, any pressure complaints and service calls. Sometimes we can take these customer feedback and customer complaints and tie them back to specific pressure zones in our systems or even specific valves. And now we can nail things down. But in order to do that, you have to integrate your data back and forth and not have these data silos where you got a little bit of customer data over here and operational data over here and they're not talking together. You can use customer complaint data to actually influence your operations and get at the core of some of the problems here. So that's important. And SCADA trends, uh, SCADA is really taking on a big role these days. We're seeing a lot more sophisticated SCADA systems, cloud-based SCADA systems, and they're doing a lot more than they used to. You can tie a lot of these things in. You can pull it up on your cell phone. And so we're going to want to take our SCADA data. You're going to want to put that into a spreadsheet. And there's a lot of ways to take this and actually automate that process even and analyze pressure patterns and anomalies. We want to look at those anomalies because that's going to tell us something. We need to figure out those anomalies. And then lastly, continuous improvement. It's rarely going to go perfect the first time. So you want to build review loops where SCADA data, field crew reports, customer feedback continuously refine your pressure management strategy. So we're really looking at the data. We're looking at those anomalies like we talked about in step 5 and determine where those anomalies are and make the improvements to deal with that so everything flows smoothly and then we can start rolling this out to other pressure zones. So you want to conduct monthly or quarterly performance reviews, adjust your modulation settings seasonally, summer peaks and winter lows, and you're going to want to look at your usage patterns there. There are, certain communities where there's a lot of vacationers come in, vacation homes, and that can affect seasonal water use and pressures too. So you're going to want to look at all those patterns and tie those back into your pressure modulation strategy. And you're going to want to fine tune your PRV set points based on field observations, build staff expertise through ongoing training and sharing the experience. And so we really want to go to, and this, if you've watched any of my videos, I go from the reactive saying we need to go to proactive, and then we really need to get into the predictive analysis. And that's where the data driven methodologies take us. So Regular data review transforms pressure modulation from a one-time project into a continuous optimization program that delivers compounding benefits over time. This is really important statement here. So, all right. So, PRV controllers and technology. Let's look at the individual types of controllers. And we have the fixed outlet, the time modulated, the flow modulated, and then we get into the smart controllers. Um, let's look at that. Our fixed outlet pressure control. That's going to be a direct acting PRV. It's going to be a simple spring and diaphragm mechanism that maintains a single fixed outlet pressure set point regardless of demand or time of day. It's really the most basic form of pressure management and also the most cheap. The least expensive. So lowest initial cost, simple installation and maintenance, uh, highly reliable. There's no electronics involved, and it's suitable for remote locations because it's a set and forget type of thing. So the limitations are obviously that it's inflexible, one set point only. You'll get excessive overnight pressures with this type of system, and which is what we're trying to get away from. A limited water and energy savings, and it cannot adapt to demand changes, obviously. So now we go into the time modulated pressure control. This is a step up because this is a pilot operated PRV with an electronic controller, and it's going to switch between two or more pressure set points based on a program time schedule. So higher pressures during the day when you're getting a lot of use in the system, and lower at night when you're getting less use. So you're maintaining a constant pressure based on the time of day. So you're going to have some historical information on, and you're probably going to have to tweak this a little bit to get the timing right on these things. But this is going to be a little more expensive than the fixed outlet pressure control, but not too much more. It's also kind of a set and forget because once you set the time, then unless you come back and reset it, it just kind of stays that way. So it's greater water savings versus fixed, relatively inexpensive upgrade, reduces nighttime leakage, and it's proven technology. It's not reactive to real time demand, obviously. It requires programming expertise, although not a lot. Fixed schedule may not match actual usage, so you're going to have to kind of pay attention, especially to seasonal fluctuations in demand, and it needs a bypass for emergencies. So best for small utilities start with pilot operated PRVs with dual set points, night and day, and then affordable entry points with immediate benefits require minimal electronics and SCADA infrastructure. So stepping up from there, but beyond that, we now get into the more complicated and more expensive, but really the more sophisticated techniques for managing pressure in your system. So, number one would be flow modulated pressure control. How it works is you're going to have a flow meter at the pressure zone inlet that's going to provide real time data to the controller. So, this is going to be an IoT or Internet of Things type of setup. And then it adjusts the PRV outlet pressure based on the actual demand from that flow meter. So it automatically adapts to demand fluctuations, increases pressure during high flow, decreases during low flow. It responds appropriately to fire flows by sensing high demand. So if you have fire flows, a lot of these other pressure controllers, the time modulated, that they can't adjust accordingly. So this can adjust to fire flows. It requires accurate flow meter and a sophisticated controller because they have to talk, and that's important. So, lastly, we have our remote wireless monitoring closed loop control, and this is kind of the gold standard of sophisticated pressure modularization, and something I mean, if you want to really do it right, this is the way to do it because it's a pressure sensor at critical low pressure point. It transmits live data via cellular or radio, and some even have LoRa types of communications to the PRV controller. The controller maintains precise minimum target pressure at the remote critical point. So you're looking at where you're getting high and low pressures in your system, and you're monitoring those and adjusting the rest of the pressure to suit that. SCADA integration enables remote set point adjustments and trends, um, and it provides invaluable system data for leak detection and proactive management. So that's really your gold standard. You're going to get maximum water and energy savings, stable pressure profile, real-time optimization, and remote management capability. It is going to be a higher initial cost. We'll look at kind of some of the price ranges here. It's increased complexity. It requires SCADA infrastructure, but quite frankly, I don't know too many small water systems, even small water systems that don't have some type of SCADA system now. Um, and advanced operational skills needed. And generally, there's going to be a training program in how to use these things. So that's not going to be too big of a hurdle to overcome. So, smart controllers deliver 15 to 30% non-revenue water reduction when properly implemented with SCADA integration. So here's a look at, here's kind of a summary of all the different types of controllers, the PRVs here. So we're going to look at the control method, the complexity, initial cost, water savings potential, energy savings, required infrastructure, operational expertise, best applications, and typical ROI payback. So we start off in the left-hand side here with our fixed outlet, and we progress across to our remote monitoring, the closed loop. That's our gold standard. And you can see the cost range, the fixed outlet, the whole program, $2,000 to $5,000 because they're very simple. And the remote monitoring for a small system, 25 to $50,000 plus. You can go up from there. So it just depends on how fancy. And the time modulated and flow modulated are somewhere in between. Time modulated, really not that much more than the fixed outlet. We don't recommend anybody go with the fixed outlet. Um, at the minimum, you should do the time modulated PRVs for your system. So, um, and the rest of this is summary of, and I'm going to leave this up here for a minute so you can get a screen cap or whatever. But this is really a summary of what we talked about earlier. You can see the water saving potential. Obviously, the more you spend, you're getting more accurate control. So your potential for reducing non-revenue waters is going to be better, um, uh, better energy efficiency. And so the best applications, generally, I'm throwing out the fixed outlet just because I don't think anybody should really be using that. Um, so time modulated, small to medium utilities, first pressure management type of project should be time modulated because you can get used to it, and then you can start to roll out some of these other ones. So predictable demand patterns is what you need for that. So um, flow modulated is going to be medium-sized utilities with SCADA, variable demand zones, and fire flow requirements. So that's probably going to apply to the small guys too. So you can see it's just it gives you more accuracy and a little bit better flow modulation than just the time modulated. A little more control, and then lastly we have our closed loop system, and that's going to be more advanced utilities that can handle that. It's going to be the most expensive. Um, and you may want to just put this on high value zones. So you could have a mix of systems actually. Complex topography where you have higher elevations, lower elevations. So you're really having trouble uh, moderating your pressure in those areas. This is where the closed loop system can come in handy and maximize your optimization goals. So typical return on investment payback for fixed outlet 5 to 7 years, 3 to 5 years for time modulated, 3 to 5 years same for flow modulated, and then generally the remote monitoring, because it's more expensive, but you're also getting the maximum savings. The ROI is going you're going to see that in about 2 to 4 years, so a little bit shorter time frame. So the higher savings offset the cost. So um, recommended path for small utilities, start with time modulated control for your first pilot zone. So you're going to want to work on that and get that concept down, generate savings. And then if you want to move on to some of your other zones and do some of these more complicated techniques, you can do that. So you may get just using time modulated, it may be sufficient to do what you need it to do if you have pretty predictable demand and not lots of fluctuations. But if you're seeing a lot of fluctuations, you may want to look at some of these more advanced methods. All right, so data-driven implementation. So we want to integrate the technology, the monitoring system, the analytics capabilities to achieve successful pressure management outcomes. Real-time data enables informed decisions, continuous optimization, and measurable results. And I'm going to go back and say one bit of data is actually a snapshot. Trends is ultimately what we're looking for is understanding our trends. So that's going to require multiple data points. All right, so the foundation of data-driven pressure management, modern SCADA systems. Um, and for those that don't know, SCADA stands for supervisory control and data acquisition, and that's kind of the heart of your water treatment plant. So they provide the technological backbone for effective pressure modularization, enabling utilities to monitor, control, and optimize their distribution networks in real time. And they, quite frankly, they do a lot of things. They monitor your wells, your pumps, and your tank levels. There's a lot of stuff that SCADA does that it didn't used to do, and these have become a lot more sophisticated and a lot less expensive too. So more capabilities for lower costs. What's not to like? So um, real-time data transparency transforms operations from reactive troubleshooting to proactive system optimization. So we're pounding that point in again to we want to go to proactive and then on to predictive analysis for our water systems. Data allows us to do that. So um, key SCADA capabilities we're looking at is real-time monitoring, alarm management, so being able to get the alarms out to the people even on their off hours, remote control, being able to adjust things by remote control, and data trends. Um, and I would also say one of the things you want to have is the real time. It's probably implicit in here, but make sure you have cloud capabilities so you can access it at any point in time. So when your operator gets an alert at home, he can call up everything on his cell phone and see exactly what the problem is before he rolls out. And that's going to be really important. And those capabilities are there. Like I say, the SCADA systems now are much more sophisticated and less expensive. They can do all those things. Um, this enables time-based and flow-modulated control strategies, reduces emergency response time through instant notifications, very important, provides documentation for regulatory compliance. You did what you said you were going to do, and cloud-based platforms accessible for mobile devices. I kind of hammered home that point, but that's really important. It's no excuse not to have that because it's all available to you. So ROI analysis in the financial case. So we have two ways of looking at this: our initial investment, or is our capital expense or capex, and our annual savings, which is going to be our operational expense or opex reduction. So with our capex, we're looking at the PRV hardware. That's going to be somewhere, depending on the solution you choose, based on what we talked about earlier, $3,000 to $50,000. Monitoring equipment, $5,000 to $3,000. That's going to be pressure sensors, data loggers, communication hardware, maybe some flow meters in there to talk with the PRVs. Installation costs $5,000 to $15,000. It's going to be labor, excavation, vault construction, bypass lines. So your typical total investment around $10,000 to $25,000 for a small utility pilot project, and then we can roll that out. Um, Once you see the ROI and the success you're getting, now you can build that into your capital improvement plan and start rolling it out. because you got reliable data that shows you're getting an ROI on this. So, OPEX reduction, so water production savings, if you're getting a 10 to 15% reduction in non-revenue water, that's going to be about two to $5,000 a year in reduction in costs. Energy cost reduction, say, $8 to $2,000 a year. Repair cost savings, if you have 18 to 30% fewer main breaks, $1,500 to $3,000 a year. So total annual savings for a small water system can be, $4,300 to $10,000 a year for a typical small utility. So that will actually produce an ROI. So our example ROI calculation here, say a $15,000 initial investment, $5,000 of annual savings. So 15,000 divided by 5,000 a year equals 3 years. And so our net benefit is going to be 5,000 times 5 years minus 15,000 equals plus 10,000. So that's going to be your ROI there. So you want to be have 5 to 10 times over your system lifetime of 20 years. So that's really what we're looking for here. So the long-term strategic value, extended asset life through reduced system stress is often the largest benefit. So sometimes those are things are a little hard to quantify, but you're deferring costly capital replacement projects by 5 to 15 years, which can really save you some money, kicking the can down the road. And it's not by guess. You're really understanding your system and you're being able to predict that and know that you can actually um, uh, defer that maintenance. And well, I don't want to say deferred maintenance. That's probably the wrong term here. But you can actually look at replacement further down the road because you're reducing the pressure and the stress on the system and extending the asset life. All right, so phase implementation plan. I'm going to go through this pretty quick. Um, we want to assess and plan. So we want to conduct the water audit using the AWWA free water audit software that's available online. Deploy portable pressure data loggers at key monitoring points. Map your system zones and identify high pressure areas. Select the pilot pressure management area, so the pressure management zone, and establish baseline metrics. What are your KPIs to measure? Phase two, we want to implement and monitor your initial capital investment with diligent measurement. So we want to install time modulated PRV in the pilot zone. That's the cheapest in capital investment. Ensure proper valve sizing and installation. Continue monitoring flow and pressure data. It's the trends that are important. Measure minimum night flow, your MNF reduction, and track leak repairs and customer feedback. And then you want to document operational changes and the lessons learned so you can pass those along and share those. And phase three, optimize and expand, scale success across your system. So you want to calculate your water, energy, and cost savings, create ROI calculation and business case, present results to the board with clear payback period. The board's going to be impressed with that because they're going to see that you get a real return on this money and based on real data. That's important to boards. It makes their decision making easy when they have the data and they can make those decisions. So prioritize additional zones for PRV installation, and you can upgrade if you did time modulated PRVs in your initial pilot zone. You may want to take a more complex area and go to the more sophisticated controllers. So and develop system-wide pressure management strategy, and that's going to be an iterative process that you're going to monitor over time and make changes as necessary. So, key success factor: use the data from your pilot project to demonstrate undeniable proof of savings with real data. So this transforms your budget conversations with your board from spending money to investing for returns because you have real data and real ROIs that you're looking at, and they can get their arms around that. All right, key takeaways and next steps. Our key benefits, cost-effective strategy. It really is. It's a low-hanging fruit. Um, Scalable implementation. We want to start with a pilot area and expand out. Um, uh, Typically, PRV pressure modularization implementation has a good ROI and a good payback period of 3 to 5 years or even less. So that's important. We're extending our asset life, and we're seeing multiple benefits: water savings, energy reduction, fewer breaks, improved service. Um, these are all the benefits of the pressure modulation strategy. Immediate action items: perform the water audit. So the AWWA, American Water Works Association, free water audit software will help you quantify your non-revenue water and identify real losses. So that's a free online tool. So you can look it up, and really that's the place to start to look at what your non-revenue water losses really are. So baseline pressure monitoring: you want to deploy portable data loggers at key locations to understand your pressure patterns and what the trends are. So not only just spot measurements, but actually the trends. You want to select your pilot zone. So you want a small, well-defined area with high pressure and a single inlet for the first project. So you control as many of the variables as possible, and then you're going to want to learn from this process and build it out from there. And if you do all those things, you're going to build internal support because people are going to see measurable results, and that's really what they want to see. So you can present the data and the business case to the board, the council for approval, and if things have gone right, then they should be happy with that. So here are some resources and support that's available: the EPA Water Technical Assistance, Water TA, Engineering Support and Funding, Application Assistance, State Revolving Funds, Circuit Rural Water Associations, and the circuit riders there. The American Water Works Association has a bunch of resources available, including the aforementioned free water audit software. Uh, USDA, Rural Development, provides a lot of funding for small water systems, um, but they can be a technical resource too. And then regional AWWA sections. So you got the national AWWA, and then you have regional sections that usually have annual meetings, and it gives you an opportunity to network with your peers and and share your experiences. Um, so we want to start our pressure modularization journey today. This is really, like I say, the low hanging fruit with a good ROI. So this is the place to start to deal with non-revenue water and put some money back into the pocket of your utility. All right, so let me go back here and let's wrap this up. All right, so that is pressure modularization, and it really is for not a huge investment. Really, something you can do to improve your system, reduce non-revenue water, and put some money back in your pocket. So, if you got any questions, my email address is here. If you like this video, like it, comment on it, share it. I answer all comments, so please. Either get a hold of me directly through my email or go ahead and comment on this video. But at a minimum, if you like this video, that helps me with the YouTube algorithms. Is great. So thank you very much, and we will see you in the next video.